Okay, so let's get started. So starting from last lecture, we start to introduce the notion of a transaction. And we start by one motivating example, right? Assuming you are building a bank, the ATM system, right, to allow the user to actually withdraw money. And if you are not being careful here, right, the user could give you essentially multiple concurrent withdrawal requests. And if you mix their instruction in an uncontrolled way, a user could actually take advantage of it to get more money than what he supposed to have, right? So we look at this very simple example to really motivate the notion of transaction. So essentially, what is missing so far is we need some way to actually group all those transactions, all those instructions together, and such that different groups, they do not have any intervention with all other groups. So essentially giving a group of instructions, the notion of transactions really try to group them together. We have one instruction to say this is the beginning of the transaction, and then you have a whole bunch of instructions you want to do, and then you end the transaction. Whenever you wrap the instruction in this way, we call this group a transaction. And once you do that, we also define a whole bunch of properties that we want from a transaction. So the first property is atomicity, right? Which means that a transaction is executed in its entirety or not at all, right? So during the execution of the transaction, if you pull the block and then your machine goes down and when you restart it, you can only see two states. Either the whole transaction get executed or none of its instructions get executed. You will never see a state in the middle. So that is called atomicity. That's one property we want from a transaction. And second is called consistency, which means that a transaction actually produces a database instance that's consistent, given an input database instance that's also consistent. It means that like transaction can only bring a consistent database state to another consistent database state. So here, consistent means that it's going to respect all of the integrity constraints that you specified. So the third property is called isolation, which means that if you have multiple transactions running at the same time, your final result should be equivalent as if all those transactions are executed one after the other. So essentially, you are going to get an equivalent result as if you only have one transaction at the same time. So that's called isolation. And the third and the fourth property is called durability, which means that if you commit a transaction, the committed changes of transaction are never lost and can be recovered even if your system goes down. Which means that as long as the system tells you, okay, you successfully committed a transaction, the result is there, right? It doesn't matter whether the database goes down, right? Whether you restart your machine, when you reopen the machine, recover the data, your result of the transaction, the effect of the transaction will be there. So we define these four properties that we want from transaction. And starting from this lecture and for the next couple of lectures, we are going to talk about how does the database system actually enforce each of these properties. So before we do that, let's try to formally define what transaction is. And then let's talk about isolation and how to enforce it. So what is a transaction? We think about the database as a fixed set of named data objects, right? So here, when we talk about transactions, we actually don't care whether we are talking about a table, a tuple, or value. We don't care. We think about database as a whole bunch of objects. They have names, A, B, C, D, something like that. Each one of these can correspond to a row, can correspond to a column, correspond to a table. We don't care in most of the discussions we are going to have. So database is a fixed set of objects. And a transaction is a sequence of read and write operations. For example, you can actually read one object A from the database to another variable, and then you can manipulate that in memory, or you can write it back, right? You can write back the value of the object B from the variable B back to the database. A transaction contains a sequence of these read and write operations. And we assume at this moment, whenever we write, the changes are reflected into database immediately. Okay, so that's our current assumption. So a new transaction starts with a special keyword called begin. And then you have a whole bunch of the sequence of read and write operations. And then you stop with two possibilities. Either you commit, which means that you want all the changes of the transaction to be reflected in your database. You say, okay, so I run this, I want all the changes be in the database. Or you can abort, right? Which means that, okay, so I have run a whole bunch of instructions, but then I realize I don't really want to do that, right? I want all the changes to be undone so that it is like as if the transaction has never been executed at all. So at the end of the transaction, I can have one of these two special keywords, either commit or abort. But all transactions must start with the keyword begin, okay? So the abort action can either be initiated by the user. The user can just say, okay, so I'm going to abort this transaction, or it can be initiated by the database system. It can actually force you to abort some of the transactions that has not been committed. And we are going to see one of such example later in this lecture, actually. So let's look at some examples. So assuming you have two transactions, T1 and T2, right? So here's a very simple example. T1 essentially read the object A from the database to a variable called T, increase the value of T by 100, write it back, read another object B into T, increase the value of T, write it back. It's very simple. On the other hand, T2 is doing something very similar. It read A, multiply the value by 2, write it back, read B, multiply the value by 2, write it back. So given this, let's assume we have one integrity constraint in my database that we really want A equals to B. Okay, assuming that's our constraint. If a database system, if a database instance is consistent, it means that in that database instance, you have A equals to B. Okay. So as we can see, first one, both of these transactions will actually respect that constraint in the sense that they are going to bring my database from a consistent state in which A equals to B to another state that's different from my input. But the invariant is that in the new database state, A still equals to B. Okay, it's consistent. It's going to bring my database from something that respecting all the constraints to something else, but also respect all the constraints. When you actually run these two transactions together concurrently, you have different ways of mixing their instructions. We call each of those different ways of mixing the instructions a schedule. For example, this is one schedule, right? You could have one way to mix the instructions such that you run all the instructions from T1 first, and then you run all the instructions from T2. And that is a serial schedule, meaning that you run them one by one, but it is still one way of mixing those instructions. And we call this as one schedule. So if you think about what's going to happen, right, it's going to contain a whole bunch of transformation of database state. For example, at the beginning, you could have in my database, I have my A equals to 10 and B equals to 10. And you follow the instructions one by one, right? You first run this, and then you increase the variable T by 100, you write it back, right? Your database state is going to change, right? You start to have database state where A equals to 110 and B equals to 10, right? You keep doing this. You read B, you increase B, you write it back, and then you start to run the first instruction from T2, right? So you're going to have a database state where A equals to 220, B equals to 110, so on and so forth. At the end of the day, when you finish running this, you end up have a database state where A equals to B equals to 220. So this is just one example. This is one schedule. And its impact on the database state. But there could be other schedules. For example, this is another serial schedule, right? Different from the first one, it's going to run all the instructions from T2 first, and then run all the instructions from T1. So similarly, it's going to have different effect on the database state. It's going to multiply by A, by 2 first, then multiply the B, right? And then continue to run all the instructions from T1. Then you have 120, 120 at the end. So this is two different schedules. Both of them are actually sequential in the sense that they run like transactions one by one. And as you can see, they are going to give you different answers, right? So if you do the serial schedule where T1 is, you run T1 first, you end up have 220, 220. If you do the other one, you get 120, 120. So which one is correct one, right? So for this course, when we talk about database, both are okay. Okay, we will have concurrent execution of transactions. We will be happy with both of them. Okay, even if you, for example, submit T1 slightly earlier than T2, right? So we will actually accept the second schedule as a correct answer, right? Both are okay. Okay, so what is not okay is if you have a database state that get a different answer from either of this, right? For example, if you have database state you're equal to 300, 300, that is not something we want, okay? So of course, both of this, as you can see, share some common property, and they are actually serial in the sense that they are actually running transactions one by one. And maybe you change the order, right? But you are running one first, and then you run the other one. And this defines the property we want in terms of concurrent execution. We want all the ways of mixing the instruction that we allow in the database going to give us one of these two different states. So to that end, we define the notion of serializable schedule, okay? So we say a schedule that is serializable if it's going to lead to the same answer as some serial schedule, okay? So this is actually one example of a serializable schedule. And here, as you can see, it's not serial, right? It's not sequential, right? I run the first 3 instructions from T1 first, then I run the first 3 instructions from T2, so on and so forth. I'm mixing them together. So at the beginning, right, you have database state, for example, 10 and 10, right? So after you run the T1 part, the first components, you are going to have 110 and 10, right? And then after you run the T2 part, you have this. You continue to run T1, then you run T2. At the end of the day, you get a database state where A equals to B equals to 220. That is the same as some of the serial schedule. That is why we call this schedule serializable, okay? And of course, not all the schedules are serializable. So this is just another example, right? So I could mix the instruction in different ways. I could run the first 3 instructions of T1 first, then I run the whole T2, then I run the rest of T1. If you do this, starting from a database state where A equals to B equals 10, what would you get? You are going to get 110 and 10, right? After you run T2, both of these will double, right? And then you increase B by 100, you end up with a state where A equals to 220 and B equals to 120. That's going to be different from both of the 2 serial schedules. It doesn't matter whether a serial schedule run T1 first or run T2 first or the other way around. It's going to be different, right? So this is actually another example of a schedule that's not really serializable. One thing that's actually interesting is serializability is not only a function of the read and write pattern, but it's also a function of the computation itself. So let's look at this example. Here, I'm actually twisting T2 a little bit. So previously, I had the T2 that S equals to S times 2, right? But here, I'm changing my T2, right? So I just say S, I increase S by 200. Okay, I'm changing the computation. And then let's look at the same schedule that wasn't serializable before, right? But if you look at this, right, if you start from a database state where equals A equals to be equal to 10, right? So after you do this, you are going to have a state equal to 310, 310, right? But if you take this kind of zero schedule, right? If you do the same thing, it's going to give you 310, 310, right? So in this case, this schedule for these two transactions with a slightly different T2 is actually serializable. But on the other hand, if you compare this with the one you saw in the previous slides, they have the same IO pattern, but one is serializable, one is not, simply because of the computation that you are doing. So essentially, whether one schedule is serializable or not is a function of the IO pattern, that is, when does the read and write happen, and also the computation. And to be honest, that's not really something we want. Because when you are building a database system and you are trying to manage all those transactions, you actually do not know the computation that's going to happen, right? So it's very hard for you to build a database engine that can really understand the computation itself. At best, you understand the IO pattern. So that actually motivates us to have a different notion of serializability that's a little bit stronger than serializability that we just defined. We want some notion of serializability that only relies on the IO pattern, but not the computation, because I don't know how to analyze computation, right? But I know how to analyze IO. So that gave us another notion called conflict serializability. And then let's try to define that here and look at a whole bunch of examples. So conflict serializability is a stronger notion of serializability that only depends on the IO pattern. And therefore, it's easier for database to handle because it doesn't require me to understand the computation. It doesn't it doesn't require me to understand what each of those instructions is actually doing. So to define conflict serializability, we start from defining the conflict of different operations, those read and write operations. So first one, within the same transaction, you have a sequence of read and write. And we say two different operations from the same transaction, they're always conflicting, okay? So the intuition is we cannot reorder them, right? So essentially, whenever two operations are conflicting with each other, intuitively, we want to say you cannot reorder them, okay? So if they are in the same transaction, any pair of operations is always conflicting with each other because we cannot really reorder them. And for different transactions, for example, you have O1, right? So that's one operation in T1, you have O2, another operation in T2, right? So we say they are conflict with each other if one of them is a write operation to the same location, okay? So if that happens, we say O1 and O2, they're actually conflict with each other. So what do we mean by conflict serializability? We mean that we say one schedule is conflict serializable if we can translate that schedule into a serial schedule with a sequence of non-conflicting swipes of adjacent actions. So this is pretty abstract at this moment, but it's going to become concrete down the road. So here, there's another thing that we need to kind of keep in mind is whenever we are talking about conflict serializability and serializability, at least in this course, also in the exam, right? We only concern about committed transactions. Okay, we assume at the end of the day, both transactions going to commit. Okay. So let's look at all those conflicts, right? So there are actually three different types of conflicts, right? So depending on the type of operations, right? So you could have a read operation from T1, you have a write operation from T2, and they actually read-write to the same place, right? You have three different combinations. So let's look at this, right? So what's the intuition behind those conflicting operations? Essentially, if you have a pair of operations that conflict with each other, the intuition is that we cannot change their execution order. Okay, so that's our intuition. So let's look at this example. You have T1, you have T2. T1 first read A, T2 read A, write A, then T1 read A, then both commit. Okay. So if you look at this pair of operations, they both read A. Okay, they read to the same place. this actually, they are not conflict with each other, right? Because there's no write, right? Remember our definition of conflicting operations, right? There need to be one operation write to the same place, okay? So both are read, it's fine, right? So if you look at this pair, right, you have the read from T1 and write from T2. So this gives you a read-write conflict, okay? So this pair of operators, the read A from T1, write A from T2, there's conflict between them. Okay, if you think about why, like what's the reason that we actually do not want this conflict, right? So it is that whenever you have this read-write conflict between two transactions, potentially, right, you could have non-repeatable read at the end, right? For example, if T1 read A again, right? When you have the current order, like read A, write A, read A, right? You could have non-repeatable read on object A. But if you swap the order, right? You say, okay, so in T2, let's write A first, then T1 read A, you swap the order of the conflicting operators, and then you do not have this non-repeatable read behavior anymore, right? Which means that whenever you have a read-write conflict, swapping the order of the two operators is going to have different type of anomalies. Okay, so that's the intuition. We want to define a whole bunch of type of conflict between pair operators such that I cannot actually change the order between them. Okay. So similarly, you have the write-read conflict, right? You could have in T1, you write A, in T2, you read A, right? So this gives you kind of a write-read conflict, right? So the high-level intuition is, why does this matter? Here's just one example, right? So hypothetically, if T1 abort at the end, right? So then T2 is going to read from essential value that have never existed, right? So essentially, but if you swap the order, if you read A first, you write A, then you abort, you actually do not have this problem, right? So as you can see, the order of these two operators actually matters, right? So for different order of them, you are going to get different anomalies. So similarly, you have the write-read conflict. If T1 write to A and T2 write to A, right? So there's a write-read conflict. So given all those conflicts, right? So intuitively, all those conflicts define the ways that two operators can cause inconsistency during concurrent executions. And given this, we can define a notion of conflict equivalent. We see there are two schedules. They are conflict equivalent if and only if, first, they involve the same actions or the same transaction, right? And second, every pair of conflicting actions is ordered in the same way, right? If that happens, we say these two schedules are conflict equivalent. So intuitively, right, if we say two schedules are conflict equivalent, it means that they actually have the same set of conflicts between all those operators ordered in the same way. And that's our intuition. We are going to see one example later, right? And then conflict serializable is actually defined as a schedule S is conflict serializable if it is conflict equivalent to some serial schedule, okay? So that also means that we can actually translate a schedule into a serial schedule with a sequence of non-conflicting swap of adjacent operations. So let's look at one example, okay? So assuming you have these two transactions, T1 and T2. T1 read A, write A, then T2 read, then T1 read B, T2 write A, so on and so forth. So here, as you can see, these two operations, read A and read B, right? So there's no conflict between them. Why? Because for two reasons, right? Both are read, right? And second, they're actually on different objects, right? So there's no conflict. So I can actually swap the order. I can actually swap the order to change this into a different schedule where I read B first and then I read A. Okay, so if you look at these two schedules side by side, they have the same set of conflicts, right? Because swapping the order between read A and read B doesn't change all the other conflicts, right? So they are still be ordered in the same way. So these two are actually conflict equivalent. Okay, intuitively, it means that they are going to have the same type of conflicts between read and read of these two operators, of these two transactions. And you can continue to do this, right? So you can take this kind of a schedule, right, that we just had, and you can find another two operators are not conflicting with each other. You have write B from T1, you have write A from T2. There's no conflicts. Why? Because they are actually dealing with different objects. One is dealing with B, another deals with A, right? In this case, I could swap them without changing my kind of how other operators are conflicting with each other and their order. Right? So in this case, you can actually swap the order again, right? You can get another schedule, right? So and these two are kind of conflict equivalent. So you can keep doing this, right? For example, you can find this pair, right? So write B and read A, yeah, there's no conflict. You can swap them and you get something like this. So these two are conflict equivalent. So as you can see, I can do a sequence of swaps between adjacent operators that are not conflicting with each other. And I can arrive at a serial schedule, right? So in this case, we say the schedule on the left-hand side is conflict equivalent to the schedule on the right-hand side. If you can do that, we say the schedule on the left-hand side is conflict serializable. Okay, so that is one example about what we mean by conflict serializable. That is, you can do a sequence of swaps of adjacent non-conflicting operations such that you can get to a serial schedule at the end. So let's look at one example, right? So look at this schedule. You have read A from T1, you have read A from T2, write A from T2, and then you write A from T1. Is this one conflict serializable, right? So in this case, it's actually not, right? If you think about why, it's because you have this pair of operations that are conflict with each other, right? You have read A, you have write A, and then you have this pair that also conflict with each other. So as you can see, there's no way you can swap all those operators such that you can get a serial schedule, because no matter how you swap them, the write A from T2 will always be in the middle, right? You can never lead to a serial schedule by swapping adjacent non-conflicting operators. So this is actually one example of schedule that's not conflict serializable. So another thing, just to give another example, right? So what are different conflict operators between commit and abort, right? So here, like now we know how to analyze the conflicting behavior between two read and write, right? What if you have commit and abort, right? So in this case, right? If you have read X in T1 and you have abort in T2, right? So there's actually a conflict if T2 actually updated X. Okay, so the intuition is that if you order the read X and abort, that's going to give you a different value. Okay, so like again, right? Conflict serializability and serializability, when we talk about it, we only care about committed transactions in this course. Okay, so we actually show the abort here because we actually want to give you an example about what do we mean by the equivalency of like between two schedules. So let's look at this example, right? You have T1, you have T2, right? T1 update A, T2 read A, and then T2 abort, right? So in this case, as you can see, flipping the order between these two operators is going to change my behavior, right? So for example, if you have something like this, so it's going to like have very, very different behavior at the end, right? So that is why the order between whether you are reading A first or whether you abort first actually matters here. So similarly, right, if you have a write operation, right, so again, it is actually conflicting with the abort operation. You cannot reorder them. Okay, if you reorder these two, you end up with very different behavior at the end. So, but for commit, right, so you have the luxury to actually reorder them. It actually won't change like the final result from your transactions. So let's recap, right? So we define what is serializability, right, which is defined by the equivalency of the result. one schedule is serializable if it leads to the same result as some of the sequential execution schedule. We also define a stronger notion called the conflict serializability. We define that by swiping adjacent non-conflicting operations. So conflict serializability is a subset of serializability in the sense that if a schedule is conflict serializable, it must be serializable, but not all the serializable schedules are conflict serializable. Okay, if you think about why, it's because conflict serializability only concerns about the conflict caused by read and write, not by the computation that the transaction is doing. But on the other hand, for serializability, you also care about the actual computation that happened. If you look at most of database systems, what is trying to enforce is actually conflict serializability, not serializability. So it's actually trying to enforce a stronger notion, because enforcing serializability is very hard because it requires you to understand the computation itself, which is very, very hard to do. So now we understand these two notions of serializability. Let's try to ask another question. That is, given one schedule, right? How can we decide whether it is conflict serializable or not? So there's a naive solution, right? So you can go back to the definition. You just try to do the swipe, right? You keep playing with like to see whether you can swipe kind of adjacent non-conflicting operations. But there's an easier way that you can do it, and that is by constructing a dependency graph. So essentially, if you have multiple transactions in the system, you construct a graph where every single transaction becomes a node in the graph. And if there's an edge from Ti to Tj, two transactions, if there's an operator Oi in Ti, is conflict with operator Oj in Tj, and Oi appears earlier. Okay, whenever you have a pair of conflicting operators, you introduce one edge in the graph. And then you check whether this dependency graph has loop or not. Okay, if there's no loop in the graph, then this schedule is conflict serializable. Otherwise, it's not conflict serializable. So now let's look at one example, right? So here I have T1 and T2. So for the very first step is try to find all the pairs of operations that are conflicting with each other. So here's one pair, right? I have write A in T1. I have so I have read A in T2, right? Yeah, there's conflict, right? They read and write to the same place. And here, so the operator in T1 happens earlier. So I introduce one edge in the dependency graph pointing to T2 from T1, okay? And then here's another pair of conflicting operators. I have a write B in T2 and I have read B in T1. In this case, the operator in T2 happened earlier, right? So I introduce one edge in the graph pointing to T1 from T2. So as you can see, there's a loop in the dependency graph, right? And in this case, this is actually not conflict serializable. Yeah, go ahead. I think we have one question.
Yeah, is the read A in the very first read A in transaction A depends between the first read A in transaction A and the write A in transaction T2? Is there a dependency there as well?
Yeah, sorry. Can you say it again? So,
yeah,
so you're concerned about this thing, right? So the first
read A, the first in T1, and so the first read A in T1 and the first write A in T2.
Oh yes, exactly. So there's also like a conflict between this thing and this thing. Yeah.
Okay, cool.
So like we should be introduce edge from T1 to T2.
Okay, cool. Thanks.
Yeah. Cool. Yeah. So when you do this exercise, you need to find all the pairs. Yeah. So here I show two pairs because that's already enough, like to give you a loop, right? Yeah. Okay. So let's try something a little bit harder, right? So we have three transactions here. We have T1, T2, T3. Is this schedule conflict serializable, right? So here, let's try to find all the conflicts, right? So we have this pair. We have T1 to, so we have write A in T1 to read A and write A in T3, right? So I introduce one edge in the graph from T1 to T3, right? So, and then I have this. So it actually introduced one edge from T2 to T1. So, and then that's it, right? So essentially that is all the conflict I have, right? So like of course, for the first read A, you also conflict with this write A, right? But of course, going to introduce the same edge from T1 to T3, right? So if you look at this, right? So there's no loop in the dependency graph, right? So it's actually conflict serializable. And once you decide this, you can actually get a very natural serial schedule that's conflict equivalent to this schedule. You just follow the dependency graph. You find the root. Here's a T2. You go to T1. You go to T3, right? So essentially, this schedule is actually conflict equivalent to a serial schedule that you run T2 first, then you run T1, T1, T3. Okay. So now let's get a little bit more formal, right? So here's a claim. So a schedule is conflict serializable if and only if its dependency graph is acyclic. There's no loop in the graph. So how to prove it? Right? We are not going to go through the whole proof, but just some intuition, right? So you prove it by two directions. Okay. The first direction, you try to prove if you have a dependency graph that is not acyclic, that is like you have a loop there, right? So then the schedule is not conflict serializable. And that's the first direction that you want to prove. So how to prove that, right? So it's just some very simple intuition is you say, okay, assuming there's a loop and you construct a loop and you try to prove, because of this loop, there's no way I can swipe adjacent non-conflicting operators such that I can lead to a 0, 1. Okay, so and that is actually the at very high level how you prove this direction. And the second direction that you want to prove is if you give me a dependency graph that is acyclic, then the schedule is conflict serializable. So this is kind of much easier to prove. How to prove that? You do induction by the number of nodes in the dependency graph. Okay, you first assume if you give me a dependency graph with k different transactions and assume this is true, right? So, and then I prove that if you have k+1 transactions, this is still true, okay? So now let's look at a little bit more examples. Let's look at this schedule, okay? So very simple one. Let's construct dependency graph, right? So we have the one from T1 to T2. You have one edge here. You have one from T2 to T1, right? So, and then you have the one from T2 to T3 because of this pair. And you have the one from T1 to T3 because of this pair. So this is a dependency graph. So as you can see, there's a loop, right? So it is actually not conflict serializable. But what's interesting is let's think about whether this is serializable or not, right? And yeah, we know it's not conflict serializable, but is that serializable? If you look at this carefully, it actually is serializable because it's going to give you the same result as if you are running T1, T2, T3, right? Because at the end of the day, all of these three transactions, they all write to A. And because you are running in the last step, you write A from T3, the whole thing, the T3 is going to overwrite all the other transactions, right? So in this case, this schedule is actually serializable because it's equivalent to a schedule that you run T1, T2, then T3. It's also equivalent to a schedule that you run T2, T1, T3. As long as you run T3 at the end, it's going to give you the same result. However, this is not conflict serializable, but it is actually serializable. This is actually one example of a schedule that is conflict serializable, and that is not conflict serializable, but it is serializable at the end. Okay. So here's the relationship. Okay. So you have kind of like here in the middle, right? You have a whole bunch of serial schedules. You run them one by one, and then it gets larger if you say, so here's all the schedules that are conflict serializable, right? Of course, it contains all the serial schedules, but also contains more schedule. And then it grows larger, right? The superset is seems to be serializable, right? So there exists kind of schedules that is serializable but not completely serializable. We just saw one example in the previous slides, right? And then you have all the schedules. So what the database is trying to do is really try to enforce conflict serializability. We want to have some algorithm, some mechanism such that whenever I'm mixing instructions together, I always lead to a conflict, like a conflict serializable schedule. So that is the goal. So how does this make how does database make it happen, right? So how does it make it happen is you have one scheduler, right? So inside your database systems to deal with the concurrent execution of multiple transactions, right? You have your transaction manager, right? So take a simple, the whole bunch of transactions, T1 to Tn at the same time, right? And then you have a scheduler to really schedule the execution such that in whatever way you decide to mix all of those instructions, at the end of the day, you always have a schedule that is conflict serializable. So we now start to talk about how does the database enforce that? And in general, there are actually two ways, depending on your view about how often a conflict will happen, right? Depending on different assumptions, you could be optimistic or you could be pessimistic, okay? If you are being pessimistic, it means that you say, okay, if I do nothing, then all those transactions going to have conflict with each other all the time. Having conflict is the default behavior. So under that assumption, we really need to proactively prevent the conflict to happen. That is, before you do anything, we need to make sure you are not going to introduce conflict. And if you take that view, right? So we are going to talk about it today, that you can actually use lock-in to prevent all those conflicting behavior. But you could take an optimistic view, right? You could say, okay, if I do nothing, my expectation would be actually most of those transactions, they will not have conflict. Maybe one in every million transactions, there's a conflict once in a while, right? But most of the time, those transactions, are doing things on their own. I'm not expecting too many conflicts between them. If you take that view, right? So then if you do lock-in, if you just prevent the transaction to do anything before it can prove it won't introduce conflict, it might introduce too much overhead, right? So here you could take an optimistic view, right? You can say, okay, everyone do your work on your own, right? But when you commit, check with me, and I will check whether you introduce conflict or not. If you do not introduce conflict, right, then I allow you to commit. Otherwise, I ask you to abort, right? You could take that view. Depending on your view on your workload, and also depending on your actual workload, right? So there's a very interesting trade-off about which one to pick, right? In this course, we are going to actually talk about both, right? So today we are going to talk about how to enforce isolation, like how to enforce conflict serializability using lock-in. And on Friday, we are going to talk about how to enforce isolation by something called snapshot isolation, right? By taking an optimistic point of view. So now let's take a break, right? So when we get back, we are going to talk about lock-in, right? If you have any questions, I'll be here to answer them. Okay, so let's continue. Yeah, we were talking about essentially two different views of how to enforce isolation, right? So you can take the optimistic view, you can take the pessimistic view, right? So given different view or different assumptions you have on your workload, you are going to have different ways to enforce isolation. So let's look at one example, right? So assuming you want to build essentially vacme.ch, right? So you want to build a vaccination registration system, right? So at the end of the day, right, you are going to have one database, right, contains, yeah, essentially all the available vaccines and also the current booking from, yeah, different people, right? And then if you really oversimplify this, right, essentially the database is going to see a whole bunch of transactions that look like this, right? So every single user is going to search the database, right, to get the list of the available first dose, right, and going to book it and then read the database again, right, try to get all the available second dose and book it, right? And then at the end of the day, you commit, you click the button, you commit, or you try to commit, right? So essentially, you have maybe like hundreds of thousands of people, right, accessing the database at the same time. But every single user, if you think about it, is actually try to do this kind of very simple transaction. And you could take different views on this, right? So at the end of the day, it's like the question we need to understand is, are we expecting many conflicts in booking, right? So assuming you ask people to do whatever they want without enforcing isolation, right? So are you expecting people have a lot of conflicts, right? So your answer could be no, right? Your answer could be okay. So maybe people will kind of pick some random slots, right? So they will do not have conflicts, right? So conflict is very rare, right? So in this case, you could take a very optimistic view, and then you are going to have a system where people just do their booking as if other people do not exist. And then whenever you commit, you click the button, you actually check whether the booking you have done is still available or not at that moment. You try to check whether you can still make the booking that you picked it, right? So that seems to be the assumption of the current system, at least last week, right? So essentially, whenever you click the button, right? So if the booking that you have is not available anymore, you are going to see this, right? So essentially, if you think about what they're trying to do, is actually try to abort your transaction to say, okay, so you'll try to commit, I understand, but you cannot. You are introducing conflict and to roll you back, right? So system going to actually enforce you to abort your transaction and then you try again, right? If you take an optimistic view, this is a system that you are going to have. And you could also take a pessimistic view. Right? You could say, okay, people really going to, for example, book like everyone try to book one slot, right? So if I do nothing, I'm going to have a huge amount of people getting aborted, right? So I don't want that. I assume conflict going to happen all the time. If you take that view, right, you end up have a very different user experience. You have very different systems, right? So you could say, okay, whenever you pick your first dose, I lock up your choice that all other users cannot have access to that anymore. And then if you do that, at the end of the day, as long as you successfully book the two dose, essentially you are able to commit, right? So however, you might need to wait a long time to book your doses because you need to wait other people like to release their lock until you can make your booking, right? You can also take that view, right? So in that case, you will not have this automatic rollback, right? Every single time you commit, you are able to, because I hold the lock on that two doses. Other people cannot do anything with that until I abort, until I commit, right? So you are always going to succeed when you commit. But on the other hand, because there are so many different lock-ins on different doses, right? So it might take you a while before you can actually book something, right? So as you can see, it's a very delicate trade-off, right? So depending on different views you take, different assumptions you are going to take, you end up have very different systems, right? So it's very complex in real world to make the right decision. For example, the second one, right, the user going to actually wait longer, right? So like before they can actually book something, right? So is that a price that you are willing to pay, right? And since we are dealing with real users, right? So which of this will discourage your user even more, right? You could wait a long time in making choices, but at the end of the day, as long as you make the choice, you're guaranteed to succeed. Or you are very quick in making all those bookings, but at the end of the day, it can fail. You need to try again, right? So it's not really clear which one will discourage your user more, right? So it's a very complex problem. When you go to the real world, we are dealing with millions of users doing the same thing at the same time, right? So in this course, we are focused on the technical side, right? We are going to talk about the mechanism for optimistic concurrency control and the mechanism for pessimistic concurrency control. When we go to the real world, when we start to build large-scale data systems, hopefully not for vaccination again, right? But when we are building the real thing, right? Try to think about what is the implication and the consequence. How does your choice going to have impact on the user experience? And what are the trade-offs? What are the price you are willing to pay? And what are the benefits you are going to get? Okay. But in this course, we are going to focus on the technical side. Okay, so let's talk about how to enforce isolation in a pessimistic way. And the way we are going to do it is by introducing the notion of locking. So from now on, so here's one of our assumptions. We assume we don't know what the transaction is going to do in the future. Okay, so we have an online system, the transaction comes in, right? It tries to run a whole bunch of instructions. I know what happened before this time point, but I don't know what's going to happen in the future. Okay, and I want to have a system to be able to deal with this. So the high-level idea is actually very simple, right? Before the system access data object X, it needs to request a lock on X, such that other transactions cannot access it at the same time. So that is our really high-level idea. And the system, the transaction, only release the lock when it's safe to do so. What do we mean by safe? It means that the execution will be guaranteed to be conflict serializable. Okay, so this is a very high-level idea, but if you really get it working, it's actually very complex, and there are a lot of delicate things that you need to consider. But at a really high level, you actually want to understand two fundamental questions. The first fundamental question is when to acquire locks. Should I acquire it right before I need access? Should I acquire it whenever my transaction started? And the second question is when to release locks, right? Should I just release the lock immediately after I do my access, or should I hold it until the end, right? So this is the two fundamental questions that we are going to understand. So now let's look at this example, right? Before we talk about our two fundamental questions. So what's happening in database is you have a lock manager, right? So that's the blue thing on the right-hand side. And you have some like two keywords, right, in database. One is lock, another is unlock. Okay, when you lock something, right, you talk to the lock manager to say, okay, I want to lock this object A in T1, for example. And lock manager going to check, so is there any other transactions holding the lock? So here it doesn't seem to be the case. So the lock manager going to give T1 the lock on A. And then T1 can do whatever it wants on A, right? So, and then here T2 say, okay, so I also want the lock on A. It's also going to talk to the lock manager. And in this case, the lock manager will going to deny this, right? So it's going to say, okay, there's another transaction holding the lock, you need to wait. And then T2 going to wait, okay? And then T1 is going to do a whole bunch of things and then release the lock, talk to the lock manager. And then at this moment, lock manager going to talk to T2 to say, okay, here's your lock, right? And then T2 proceed. And then at the end, T2 release the lock and both transactions commit. So this is our mentality model when we talk about lock manager in this course, okay? So there are different ways to deal with this, but this is our assumption. Whenever I'm kind of acquiring a lock, if there's some other transactions holding that lock, the lock manager is going to ask me to wait, and then I'm going to wait. Whenever that lock becomes available, the lock manager is going to let me know, then I proceed, okay? So that is our way of thinking, a very simplified way of thinking about lock manager. Okay. So as we can see, we can use lock-in to enforce a serializable schedule, right? So let's look at this example, right? So in this example, all the access of T1 on A must happen before all the access of T2 on A, right? So because in T1, right? So whenever so before I want to read and write on A, I acquire a lock. And then when I'm done with A, I release the lock, right? So if T2 want to access A, it need to wait until everything I want to done A is done, right? If you think about all those conflicting pairs, because of I have this lock-in mechanism, right? It's actually enforced in my dependency graph. All the conflicts must, at least on A, must happen from T1 to T2, right? Fundamentally speaking, this is what's going on. Because I'm having the lock, I'm actually enforcing my dependency graph look like in some ad hoc way. In this case, like it's always there's a, if you're talking about A, all the conflict caused by A must point into T2 from T1 because T1 have the lock first. It never go the other way around. So that's a high level intuition about why lock-in can actually enforce conflict serializability. So there are different type of locks, right? So we talk, there are different type like how depending on when to release locks, when to like acquire locks. So there's something called two-phase lock-in that we are going to talk about. There's also something called strict two-phase lock-in, right? So there's kind of different ways to deal with deadlocks, right? Two transactions wait for each other, no one can make any progresses, right? You also need to deal with that. There's different granularity of locks, right? You can lock each tuple, you can lock a table, right? You can lock the whole database, right? So there are so many things that we need to understand. And then let's go through them one by one. Okay, so that is what we are going to do today, a little bit on Friday. So first, there are different type of locks. In database, there's the share lock, right? So whenever you want to read something, you can say, I want to share lock, right? So on this object. And then if there's another transaction want to read the same thing, I will allow it to do so, right? But you cannot update it. So it's actually required for read operation. And there is something called exclusive lock. It's whenever I want to write something, I can actually acquire kind of exclusive lock for write operations. Okay, so the intuition is that if all of your operations in different transactions are read operations, okay, then they can just run concurrently, right? So, and that's just one simple example of separating read and write can give you potential benefits. And in database, we always think like this kind of log table, right? So on one dimension, for example, each row depends on like kind of specify which type of lock you are acquiring, right? Here, for example, you are request a share lock, but if there's another transaction also holding the share lock on the same object, I'm going to grant the lock to you, right? If there's another transaction holding an exclusive lock on the same object, I'm going to deny it. If you are requesting an exclusive lock, right? If there's another transaction holding share lock, I'm going to deny you. If there's another transaction holding exclusive lock, I'm going to deny you. If there's no transaction holding a lock, I'm going to grant anyway, right? So in database, we actually have different type of locks, and we are going to actually look at it more in like actually on Friday, right? But if you think about this, why do we need this multiple type of locks? It actually can help us to increase concurrency, right? It can actually allow to concurrent read, right? So, and if you think about operating system, we always make that comparison, right? So why cannot operating system do something similar, right? So here again, right? Database knows the semantic of operations. Whenever I'm acquiring a lock, I actually know what I'm going to do in the future. I know I'm only going to read it, or I'm only going to write it, right? So then I can have actually more information to allow the system to do more optimizations. Okay, so it's very similar to buffer manager, right? Because database knows about the query, it actually can pass on more information to allow the system to do more optimizations. So in practice, there are actually a whole bunch of other lock mode in real systems. So here we will only talk about two of this: shared lock, exclusive lock. On Friday, I'm going to show you a very large compatibility table of different locks in real systems, right? But we are not going to talk about it. It follows the same principle, right? Okay, so here's a very important statement. So locking, if not being careful, will not give you conflict serializability. That is, not all locking strategies can give you conflict serializability. So let's look at one example, okay? So in this example, I have T1 and T2, right? So at the very beginning, T1 requests exclusive lock on object A. In this case, because there are no other transactions holding the lock on A, the lock manager going to grant it. And then T2 want exclusive lock, okay? So yeah, going to get denied. And then T1 going to read A, write A, release the lock. And then T2 get the lock, write A, and then T1 change its mind. Yeah, I actually want to read A again, right? I want to do something. In this case, T1 going to acquire the log on A again. Here, because only want to read it, is going to try to get a shared log, get denied, because they need to wait for T2, because T2 is holding the log. And then T2 say, okay, I'm done. I unlock A. Then T1 get the lock, it read A, it unlock A, both commit. So if you're not being careful, this is entirely possible, right? But if you think about this schedule is not conflict serializable. Why? Because if you look at this pair, right? So T1 read A, write A before T2 write A. And then you look at this pair, right? T2 write A before T1 read A, right? So clearly, if you define the dependency graph, there's a loop, right? So it means that by just holding the log, protecting your read and write is not enough. It's actually important for you to decide when to acquire the log and also when to release the log, such that you are going to enforce conflict serializability. One way to do that is by doing something called the two-phase locking. It's actually partition the transaction into two different phases. In the first phase, it's a growing phase. And in that phase, each transaction can request locks that it needs from the lock manager, but it cannot release locks. Okay, so it can only acquire locks. And the second phase is a shrinking phase. And that is the phase that transaction is only allowed to release locks that is previously required, but it cannot acquire a new lock anymore. So if you look at the figure on the right-hand side, right? So the x-axis is time. The y-axis is essentially how many locks that the transaction hold, right? So you can see there are two phases. In the first phase, it can only acquire lock. And then in the second phase, it can only release lock. Okay, so this is two-phase locking. So let's look at one example, right? So here, I have T1 and T2, right? T1 first can acquire exclusive lock on A. T2 acquire exclusive lock on A, get denied. T1 do whatever, release the lock. T2 get the lock, do something, release the lock, both commit. So this is actually one example of a schedule that is allowed by two-phase locking, right? Because as you can see, both transactions, so for T1, it kind of acquire the lock first, and then do something, release lock. It will not acquire lock in the second phase. T2 the same. The first phase is acquire lock, and then in the second phase is release lock, but you are not going to acquire new locks after it's released its first lock. Okay, so it's naturally partitioned into two phases. There's a growing phase, there's a shrinking phase. In the growing phase, you acquire lock. In the shrinking phase, you release lock. So here's the fundamental claim about two-phase locking. That is, if you do two-phase locking, it's going to guarantee conflict serializability. So that is, it only allows or generate schedules whose dependency graph is acyclic. So let's think about a little bit why, right? So essentially, all the conflict of on the same object A will be from T1 to T2 if T1 acquires lock earlier than T2, right? Why? Because once T1 release the lock, it will not touch A anymore because I'm not allowed to acquire lock again, right? So once I release, I'm done, right? Essentially, all the edges in the dependency graph, if T1 acquire lock earlier than T2 on A, will always be from T1 to T2, right? It's never go the other way around. If you look at different objects like the A and B, right? If there's an A from T1 to T2 and there's another object from T2 to T1, this is not really possible, right? And you can actually take a piece of paper and try to draw it. It's not always possible. In the worst case, it's going to give you a deadlock that they are waiting for each other, right? But otherwise, you will never have the case where T1 acquire lock on A before T2. On the other hand, T2 acquire lock on B before T1, right? So in the worst case, it will be a deadlock, right? So otherwise, this simply cannot happen. Okay. So essentially, when you have a schedule that can be generated by two-phase locking or kind of allowed by two-phase locking, you can actually enforce conflict serializability. So what is the problem here, right? So if you think about this, there's one potential problem about two-phase locking called cascading abort. And here's one example. Assume you have two transactions, T1 and T2, right? So if you look at this schedule, right, empty is allowed in two-phase locking, right? For T1, it try to get the lock, read and write A, unlock A, and it doesn't acquire lock again, right? So for T2, the same. I acquire a lock, I do something, right? So it's allowed in two-phase locking. However, if you think about this abort, right? So assuming T1 unlock A, and then it abort. So what would happen, right? So in this case, database need to undo all the changes done by T1. However, if you look at this read operation, right? Because it happens after T1 unlock A, it's going to read from T1 in the sense that this read A is going to get A that is written by T1. But now I want to abort T1. It means that I also need to abort T2 because T2 is reading something that has never existed in my database if T1 is rolled back. This is called cascading abort. If you do two-phase locking, it is entirely possible that you abort one transaction is going to trigger the abort of another transaction. Okay. So, and it even gets worse because think about this. What if T2 committed before T1, right? So it is entirely possible, right? If you do two-phase locking, this schedule is possible, right? So you have the growing phase, you have the shrinking phase, everything is fine. But what if T2 commit and then T1 abort, right? So in this case, it will have cause problems, right? Because T2, I need to roll back T2 because T2 is reading something that doesn't really exist in my database. But T2 committed, right? So I need to force the abortion of a transaction that's already committed. So I do not have durability anymore, right? So this actually causes a pretty big problem because I cannot implement all four properties that I want from a transaction because I cannot have durability. Even though I tell you, okay, T2 committed, but tomorrow I get back to you, okay, I need to abort that. Sorry, because some other transaction aborted, right? So that is a violation of durability, right? So we don't want that. So we need to do something to improve two-phase locking. And one way to do that is do something called strict two-phase locking. It's very similar to two-phase locking, but a very small twist. So again, you have two phases. You have the growing phase, where each transaction requires a lock, and it cannot release locks in the growing phase. And then it's going to keep all the locks until the very end of the transaction. Either it's commit or abort, it doesn't matter, but each transaction is going to keep all of its locks. And then until the very end of the transaction, it's going to release all the locks. if you do this, this is a strict two-phase locking. If you think about like a kind of like the figure on the right-hand side, right? X-axis is time, Y-axis how many locks that each transaction hold. Is going to keep growing, and then at the end of the transaction, it just suddenly releases all the locks. Okay, so this is strict two-phase locking. So let's look at one example, right? So on the left-hand side, right? So we see this example that this schedule is allowed in two-phase locking, right? However, it's not allowed in strict two-phase locking. Why? Because you are not holding this lock until the very end. There's a window here. That's not allowed. In strict two-phase locking, right? You hold all the locks until you are done, right? So this is just one example that this unlock and this abort will always happen together. Okay, so there's no window between unlock and abort in strict two-phase locking. Okay, so if you do this, you can see that you will not have the problem of cascading abort, because whenever you are aborting T1, right, T2 cannot be committed yet because T2 is waiting for that lock, right? So that is actually why strict two-phase locking can actually to help you to get rid of the problem of cascading abort. So now let's look at this example, right? And think about whether the schedule is allowed by two-phase locking or whether it is allowed by strict two-phase locking. So first one, can two-phase locking generate a schedule, right? Let's think about this. Yeah. So here, if you look at T1, right? So what it's doing is acquire a lock, read A, write A, unlock, and then acquire a lock again. Of course, this cannot happen in two-phase locking, right? Because you don't have the growing and the shrinking phase, right? So this is actually not allowed by two-phase locking and clearly cannot be generated by strict two-phase locking, right? So how about this? For this schedule, is this allowed by two-phase locking? So let's read this, right? So here what happened, T1 going to acquire a lock, do something, acquire another lock, do something, release lock, commit, right? So there's a growing and a shrinking phase, right? Before this point, before it is acquire lock, after this, it's release lock. Let's look at T2. It's acquire a lock, wait a while, acquire another lock, unlock it, do something, commit, right? So yeah, so there's the growing, there's the shrinking, right? For both transactions. So this is actually allowed by two-phase locking. But is it allowed by strict two-phase locking? Actually, no, right? Because if you look at T2, once you release the lock, you actually have something else to do, right? Before you commit. So that cannot happen. In strict two-phase locking, you need to keep your lock until the very end of the transaction. So this is actually not allowed by strict two-phase locking. So let's look at this one. It's very similar to the previous one, but now I swapped this instruction with this to unlock, right? So, and as you can see, right, can two-phase locking generate this? Yes, of course, right? Can strict two-phase locking generate this? Yeah, yes, right? Because I'm holding the lock until the very end. So this is kind of the example about two-phase locking and strict two-phase locking, right? Both of them can give you conflict serializability, right? So it only allows schedule that the conflict is serializable. So you have the isolation. But the downside is if you are doing two-phase locking, you have the problem of cascading abort. Then it actually stops you from implementing other properties that you want in transactions, namely durability. Okay, so now we talk about a whole bunch of good things about strict two-phase locking. What is limitation, right? So here's one example. Let's look at this. Assume you have T1 and T2. T1 first acquire lock on A, and the lock manager gave it the lock. And then T2 try to lock B is also fine, right? So no other transaction holding lock on B. So lock manager going to grant the lock. And then T1 do something on A and then try to lock B. And then T2 do something on B and try to lock A. In this case, both are fun, right? So if you do strict two-phase locking, this schedule is perfectly fun, right? However, if you think about who is waiting for whom, when T2 try to acquire lock on A, it's going to wait for T1. And for T1 try to acquire lock on B, it's going to wait for T2. In this case, these two transactions are going to wait for each other, and none of them can make any progress, right? Essentially, they're stuck, right? So that's called deadlocks, right? And that's a potential problem for strict two-phase locking if you're not being careful. So what should we do? Well, there are actually different ways you can deal with this. The most popular way, actually not the most popular way, probably the simplest or the most natural way, is to periodically automatically detect deadlocks. And if there's a deadlock, the system can issue the abort on some of the transactions to roll them back to break the deadlock to allow other transactions to make progress. If you take this view about how to handle deadlock, which is not the only view, right? So, but if you take this view, there are two questions we need to understand. The first question is how can we detect deadlocks? And second one, how can we pick which transaction to kill, such that I can break the deadlock to allow other transactions to make progress. So let's talk about detection. Detection is actually relatively simple, right? You can construct a waitful graph, right? So each node in the graph is a transaction. If there's an edge from T1 to Tj, it means that Ti to Tj, it means that Ti is waiting for a lock currently held by Tj, right? So, and then the system has a deadlock if there's a loop in the waitful graph, right? Which is very natural. So assuming this is the current state of the system, T1 waits for T2, so you have one edge in the waitful graph from T1 to T2, so on and so forth, right? You can actually build this graph by yourself. And then you can see, do I have loop here, right? In this case, T5 is waiting for T2, T2 waiting for T3, T3 waiting for T5, right? There's a loop, so there's a deadlock, right? And periodically, your database can actually do that. And the lock manager can actually hold this graph, right? So this is another example, right? So get back to this example, right? So here, right? So T1, T2 is waiting for T1, right? So there's a one edge from T2 to T1. T1 is waiting for T2. There's an edge from T1 to T2. You'll see there's a loop, so there's a deadlock. So it's relatively simple, right? So it's relatively simple to about how to detect a deadlock. So once there's a deadlock, how can we handle it, right? So once you construct a waitful graph, check deadlock, once you realize, there's a deadlock, what should I do, right? So the fundamental thing is you need to kill some of the transactions. Right? You don't really have other choices. You need to pick one transaction to kill. So which transaction to kill is actually a very interesting research problem because it's not really clear how can you prioritize that. So you could prioritize by age, right? Maybe you just kill some really newly submitted transactions, or you can kill some very old transactions. Interestingly, we can make argument to both, right? So sometimes, for example, you want to kill a very new transaction because it hasn't done much yet, right? It's actually hasn't done many computation, hasn't done any IO, right? So maybe if I kill it, the user don't demand too much. But you can also make an argument that we should kill the old transactions. Maybe that transaction has some problem. It's touching too many things, right? So it's a keep waiting. If I kill that, I can free up the space for a whole bunch of other transactions. That's entirely possible, right? So you can make an argument either way. That's why the problem is actually very, very interesting, depending on your assumption on your workload, right? So you can see how much progress, right, each transaction is making, right? So maybe there's one transaction just one step away from being done. Maybe I do not want to kill that, right? So you want to check how many items are being locked, right? Maybe there's a one transaction holding a whole bunch of locks, right? Maybe you want to kill that. So, and also how many deadlocks a transaction can break, how many potential rollbacks that you are going to have, like how many times the transaction being aborted in the past, right? You do not want to have a system that keep aborting one transaction again and again, right? Maybe you want to have some kind of fair schedule between like which one to kill, right? So there are a whole bunch of considerations goes into deadlock handling, right? So in a real system, you are going to pick some point in the trade-off space. How can we pick that point, right? So I think right now you are pretty familiar with our strategy is come up with an assumption on your workload. This is what I assume about the workload and try to define the end goal, right? So this is the thing I want to optimize in that workload. And then naturally, you are going to see the cost and benefit for different strategies, and then you'll pick the one that makes sense for you, okay? Okay, and in real database systems, this is actually something that you can actually tune, okay? Okay, so that's all that we have for today, right? We talk about essentially a precise definition of transactions, and then we talk about essentially different notions of serializability. And we talk about one way to enforce conflict serializability, that's by using locks. So on Friday, we are going to talk more about locks, and then we are going to talk about the different view on concurrency control. Is instead of being pessimistic, just you need to have lock before you can do anything, we want to take a more optimistic view. That is, you can do a whole bunch of things, but check with me at the end. That's called snapshot isolation. And we are going to talk about that on Friday. Okay, so that's all for today. If you have any questions, I'll be here to answer them. Otherwise, I'll see you guys on Friday. Okay, so is there no questions? See you on Friday.